dimension, and we computed the Hausdorff dimension for the middle 1/3 Cantor set. Yeah. Now, um, in the proof while we were computing the Hausdorff dimension, we've seen that obtaining the upper bound was actually pretty straightforward, right? And we just had to find a very nice cover for the set, and using that cover, you were able to give an immediate upper bound for the dimension of the set. So I'll just record, this neat argument, which comes from that proof. So suppose F can be covered by nk many sets of diameter delta at most delta k with the limit of delta k is 0 as k goes to infinity. So in the case of the middle third Cantor set, this was nk was 2 power k and delta k was 1 by 3 power k, right? Then the Hausdorff dimension of f is bounded above by log, sorry, the limit of log nk divided by log delta k inverse. Yeah. Now, I'm not going to prove this proposition because we have seen how this works in the case of the middle third Cantor set. Is this actually visible? For those who are online. Yeah. Okay, great. So proof is pretty straightforward. So I'm going to leave that as an exercise. Now, what I want to, oh yeah, maybe I can mention few more things before we move to the next topic, um, which is that using the argument with which we have computed the host of dimension of the middle third Cantor set, there are various other kind of sets that we can study. An immediate generalization from the middle third Cantor set would be what we call, um, say, take this example. We call it the middle 1 minus 2 beta Cantor set. So the construction in this case would be recursively by taking E naught to be the unit interval again, and E1 to be 0 to beta union 1 minus beta to 1, where beta is a quantity, a real value that's strictly smaller than half. Okay. So each time I, at the level k, you choose one of the net intervals at the level k, and then you keep the first part of this first interval whose length versus the length of the kth net interval is beta. The ratio of these two lengths are beta, and similarly you keep the last end as well. So this is an immediate generalization of the construction of the Cantor set. Um, so ei is going to be a union of 2 per I intervals of length beta per I. Yeah. And E is defined to be the intersection of all these guys. So with this construction, and by the argument that we have seen yesterday, it's quite easy to see that the dimension of E is log 2 by log 1 by beta. Yeah. And if I call this guy as beta, then the HS beta measure of this set is in fact 1. Okay, so that's another example where we can run yesterday's argument. I can list out various other Cantor sets constructions as well, but instead of that, I think it would make sense to discuss another method, through which you can compute using which you can compute the dimension of a set. So, I mean, you can see that in the argument that we have seen yesterday, it was very construction specific. It's of limited use because of primarily because of that. Because then you really have to get into the nitty details of the construction to compute the Hausdorff dimension of that set. Okay. Um, so to moving away from that kind of an argument, um, we 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 go back to we ask this question. Okay, so if I look at the dimension, if I'm trying to compute the dimension of a set, what is the issue that we have? What is the difficult part? We have already seen that obtaining an upper bound should not be that difficult, right? Because I just have to find a really nice cover for the set, and using the lengths, the sizes of the interval of the sets, the diameters of the sets in that cover, I should be able to obtain some upper bound for the diameter. For the lower bound, however, I should be able to say something about the sum of the nth power of the diameters for an arbitrary collection, right? That's the issue. Now, what can cause, what can help you, or in what situation can you say that there exists a lower bound to this S sum? This happens, for example, when an individual set, say U, uh, cannot cover a big chunk of the set E, where E is the set whose dimension we are trying to compute. So I'm saying, if I start with the individual set U. um, I want to say that the set U cannot cover a large chunk of the set E without the size of U being large. Yeah, and the size is measured as the nth power of the diameter of the set, diameter of U. Okay, and one way to make this statement, this vague statement, mathematically precise, is by stating something called the mass distribution principle. Okay, we are going to construct a measure on the set E, such that let's say mu is the measure that we are going to construct, such that when I compare mu of U with the nth power of the diameter of U, there's always an inequality. Like the nth power of the diameter of U must be bounded below by mu of U. So that's the kind of inequality that I'm going for. Okay, so making I mean, if that description was vague enough, let me make it mathematically precise. Let mu be an outer measure supported on E or F, I think. F and suppose for some S there exists a constant C and an epsilon positive such that the measure of U with respect to mu is bounded above by the nth power of the diameter of U. Okay, and this holds for all sets U with their diameter at most epsilon. Okay, so this is um, yeah. So this I mean this is in a way I'm trying to see how F is spread in space, right? If this is the case, no, I don't need U to be. I'm sorry. I need mu to be supported on F. Yeah, yes, that's right. Yes. No, that's correct. So as I was saying earlier, I'm trying to see when, I'm trying to look at how much of U intersects with F. Okay. And I mean, you could think of this portion as a measure of, how much mass is there in U intersection F. Okay. And you're saying that it will be controlled by the size of U. Then it's a zero. That's it. Yes. So then,
By supported on F, you mean that any set which is disjoint with F has measure zero. Is that what?
yeah, I mean, if you by supported, what I mean is that if I take any function whose support is who's compactly supported outside my set F, then mu acting on that function will give you zero. So yeah, whatever you're saying.
Let's have a second to process.
Yeah, yeah, yes, 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 that's right. Yes, but I'm sorry. Yes, that's it. That's correct. Yes, thanks. Then Hs of F is bounded below by mu of F divided by C. Okay. In particular, if mu of F is positive, then I get that the S-dimensional Hausdorff measure of F is positive, and therefore S must be a lower bound to the dimension of the set. So as I was saying, sorry, I'll just come. So as I was saying, I'm going to use this proposition by constructing a measure, right? Now this measure will be constructed, depending on how f is spread, as I was saying, right? It is closely related to the spread of f, or how the mass of f is spread. Yeah. But this proposition doesn't really care about that. It just says that if I'm starting with an arbitrary measure supported on f, and if this condition, if this growth condition, ball condition, or this inequality is being satisfied, then I have this lower bound on the s-dimensional Hausdorff measure of the set. Yeah. And once I have this, if in addition to that, if mu of f is positive, I mean, for this result to hold, I mean, mu can be the zero measure as well, the first part. Yeah. But in addition to that, if mu of s is positive, then I'll see that the s-dimensional Hausdorff measure of f is positive, and therefore s is a lower bound to the Hausdorff dimension of the set. So that comes from the definition.
Particular thing, whatever you're saying.
Yes.
Not going to be a question for me is that if
Yes.
not,
Yes. Yes.
we have to still say that mu of f is positive. Okay. Down below.
Sorry, I didn't answer.
Now I'm
Really
only
understand.
trying to say that if mu is not a zero measure and
Yeah.
it's supported on it,
Yes.
so outer
Then
it's not a zero outer
wouldn't
measure.
wouldn't mu
it
of
is
f be
supported on
positive then? Wouldn't mu of f be positive then?
thing. So that a redundant thing. That is all that I'm asking.
Yes.
Yeah,
Yes. That's right. Yes. 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 Yes.
that's fine.
Yes. Okay. Is the statement clear? Yeah. Okay. Now the proof. You take any cover, for the set f. With the diameter of ui being bounded above by epsilon for all I. Then mu of f um, is bounded above by mu of union ui, and that's bounded above by sum of mu of ui. And here I just use this inequality, and um, now I see that if you recall the definition of the S-dimensional Hausdorff measure, right? You're looking at the infimum over all these S sums. Yeah. So this inequality would tell me that mu of f is bounded below, bounded, is a lower bound to C times HS delta of f for all delta uh, smaller than epsilon. And now by taking the limit as delta goes to 0, I get this lower bound. Yeah. And the second part is clear, right, from the definition. Okay. So using this, so this is using the mass distribution principle, we are now going to compute. Yeah, go on.
So this I followed, and I seem like I have some intuition that I was calling it the mass distribution principle, and what you had said about intersection with that. Could you repeat that?
Yes. So I mean, actually, so in the we are going to see how I'm going to apply this, principle, right? Because right now it's not clear to me where this mu is coming from, or how mu is related to how, as I was saying, the mass spread or the mass distribution of F. You see, we'll see that in the specific constructions that we are going to look at. Um, like in order for mu to satisfy this inequality, it has to be related to the distribution, the mass distribution of the set F. Do you have a comment? Yeah. Okay, so we will see that in the next example. Okay, um, so what I want, I'm going to look at certain, say, Cantor type sets of arbitrary dimension in R, and we would like to use the mass distribution principle to compute the host of dimension of these sets. So I choose S in 0, comma, open interval 0, comma 1. And just like the middle third Cantor set, I'm going to, define this Cantor set in a recursive fashion. So we start with A0 being the unit interval. And we will define uh, these EJs as a union of disjoint closed intervals um, by specifying um, the components of EJ intersection I, where I is a uh, is an interval at the j minus 1 level. In other words, I is an interval that one of the net intervals that constitute EJ minus 1. Okay. So take how am I going to describe this components here? So take I in EJ minus 1. Now for each of this I, I'm going to choose an M. Now this M can vary depending on I, and some and M many closed intervals. Yes, that's right. That's right. Yes. And okay, so this choice will be done in such a manner that these JIs are equally spaced and they are of equal length. Not done with, it's a long construction, m times, say, as I've said, each ji is of the same length. So m times ji power s is actually equal to the size of I power s. Okay. I wanted to think about the Cantor construction, right? In that case, um, m m was always equal to, what was m? 2, right? So at the jth level, you choose two subintervals. In this case, at the jth level, I mean, the number of subintervals that you're going to choose will depend on which interval that you are standing at. Yeah. Or I mean, I'm allowing the generality basically. So this is a more general construction in that fashion. And the left endpoint of J1, the first interval, coincides with that of I. And similarly, the right endpoint of Jm coincides with that of I. In other words, if this is I, uh, or maybe I can draw two such levels. At the first level, I'm going to choose three intervals. And in the last time I did this, we lost video. So let me be careful. And so in the first level, I'm choosing three intervals, okay, from 0, 1. And in the second level, for the first interval, I'm going to choose, say, only two subintervals. And for the second interval, I'm going to choose three subintervals. And here again, I'm going to choose two subintervals. So it's, I'm allowing some like game with some flexibility in its construction. So yes,
See, that equation,
yes,
not quite sure
yeah.
whether they have to mod I power, you have to choose length
So,
in such a way mod I power s by mod k I power s is an integer. What makes you think you can do that? Right?
that's right. That's right. You have to make the choice. As in, so your question is, if I'm starting with an arbitrary integer, can I?
So that
Yes,
started
that's right. Yes. So I start with an s, and then so I fix I, and then I look at. I mean, yeah. So then I choose m as well.
I power s mod k I power s must be an integer somehow.
Yes. So once I choose m, the length of these guys are going to be fixed. But then you're right. I mean, then I'll have to think whether I'll be able to equally, like I'll be able to place them with equal separation.
Why don't you say that it's approximately some kind of error? It can go to zero in the long run. That's the
You're saying it because you don't think I can actually construct in this fashion. Is that the reason?
if S is irrational, for example,
Yes.
lengths are rational numbers.
No, I mean, like, see, I understand the concern. So, I mean, at least from what I've understood is it's this, right? So I start with
Ah,
once I fix an m,
ah,
you are asking, I mean, see, once I fix an m, the value of the length of ji will be fixed, right? Because of this inequality, because of this equality. Yeah. So are you asking, okay, so one, I mean, I have fixed the size of ji as well. Now, is it possible for me to find m many of them inside this interval? I claim yes, you can actually find m many of them. S is strictly smaller than one. Okay, so I think, I mean, I've done this calculation before, but I mean, yeah.
May be that the size of GI may be greater than m times, sorry, m times the size of GI may be greater than the size of I, right? So we need to fit it inside I.
That's
But
right.
that won't happen because
Because
MTS is less than M.
exactly, yeah, yeah, yeah.
Yeah.
So I think it's okay. Yes, yes.
I didn't understand the issue. Uh, understand what the issue could have been.
See,
Because from what I understood here, we have some I that
hmm,
is given, that
yes,
is forced on us, and we are choosing some M.
yes.
Uh, then
So the
by
moment I choose m, the size of ji will be fixed.
it will be fixed like this, right?
Sorry.
Like there will be a J which works also.
Yeah, of course, of course, of course.
Yeah.
But then I'll be able to find m many. I will be able to find m many intervals of this of that length inside I, right? And I have to place them, with equal separation.
Okay, okay, and then like
Yes, I think on that matter, the fact that s is strictly smaller than
yeah.
one helps. It's worth checking this, okay? Because I remember I've done this calculation before. I don't have it over here. Yes,
Also, sorry, so the goal here is to create a set of arbitrary but that formula you've given for the middle 1 by, I mean 1 minus 2 beta
here, yeah,
intersects,
yes.
that covers every value of S between
Yes,
0
it
and 1.
does. It does. This is just another construction where that has arbitrary dimension. That's a good point. Yes, this one actually gives you.
There's something
Yes. I'm sorry.
there's something we're trying to get out of this construction besides simply arbitrary dimension.
Well, it's, as I said, it's a more general construction. It covers a large class of kind of sets, unlike that one. So yeah. No, I mentioned this example here because once we discuss the argument for the middle third Cantor set, it's pretty straightforward to see how you can compute the dimension for this particular set, but not for that one. That one is going to be a bit more difficult, right? But okay, so I choose the jth level intervals. Yeah, sorry, the jth level intervals in this fashion, and then we define EJ by requiring that EJ intersected with I is the union of all these JIs. Yeah. Now let curly IJ as before represent the collection of all subintervals, all, or say all net intervals in ej. Yeah. So that's a notation that we have used earlier as well. Now, the theorem. Uh, yeah, well, sorry. I still haven't defined E. So E is going to be the intersection of all EJs. I mean, clearly these EIs form a nested sequence of sets and nested sequence of closed sets, and then you look at the intersection of all these guys. So the theorem is that for the set that we have just constructed, its host of dimension is S. And the S dimensional host of measure of E is actually equal to 1. Yes.
EJ to equal the union of the JI? Because here you can add extra things that are not in I.
Can you repeat that question?
We just require that EJ satisfies this equation, then
Yes.
you can add things in between the.
No, but see, as I was saying, I thought I had made that clear here. So EJ it consists of only these intervals. So the definition of EJ is made in such a manner that, like, I mean, I only have to describe what is going to be there inside EJ intersection I. There's nothing else. It's just
EJ equals union.
yes, 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 yes. Sorry if that wasn't clear. Yeah, yeah, yeah. Yeah, there are no additional intervals coming into picture. It's just JIs, from coming from each different I. Okay. Proof. All right. So as I was saying, I want to apply the mass distribution principle here. So I want to construct a measure mu on E. Okay. Goal is to construct a measure mu on E, satisfying this inequality, which let me call this inequality the growth condition, okay, or the S growth condition. Okay, and this is what I mean by the S growth condition. So I go back to the definition of the S-dimensional host of measure, okay, and I slightly modify that definition. So I'm going to for F in this is what I need to say, for a subset of E, I define mu of F to be the infimum over all the S sums where F is covered with these IIs, and each each II is a net interval, okay? Where F is the union of all curly IJs, the collection of all net intervals. I think it should be I0. Yeah. So you can actually see that, yes. Yes.
Expanded to the base 3.
Yes. Yes.
And then went there. by the binary expansion kind of thing and got the push forward method from the Lebesgue method, right?
Okay. Yeah, 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 yeah. I think they'll match, right? So in the case of yes, but is it possible for you to like? I mean, I see what you're doing for the Cantor set, but in this case, can I describe every point in the final set in the? Okay. Yes. Right, 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 right. So yeah, you're saying that for a very specific construction, aren't you?
That is going step. You push
Mm.
forward in
Yeah,
that particular
yeah, yeah.
by
Okay, okay, okay. Yes, 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 yes. Yeah. Now we can discuss that. All right. So I want you to see that this measure that we have defined is in fact my, if you recall the first lecture, we had defined this psi, we have defined, introduced the character theory construction. And this is precisely the measure that you get out of the character theory construction. Um, it's just that, I mean, the family that you are choosing here is the collection of all net intervals. Yeah. Now, it's true that in character theory construction, you also, you're taking the infimum over all sets of diameter at most delta, and then you're taking the limit. But in this case, you don't have to do that because, there is a nesting property, yeah, between different levels of the net intervals. Yeah. So we have seen a similar phenomenon happening in the definition of the d-dimensional Lebesgue measure, right? Okay, so once you verify this property, you can, we immediately see that the S-dimensional Hausdorff measure of the set the set E is bounded above by the mu of A. Okay, if this is true. Yeah, I'll just write it down here. Because in the case of the S-dimensional Hausdorff measure, you had a larger class of covers, right? And here I'm sticking to the covers formed by the net intervals. Yeah, so this inequality follows from definition. Yeah, I mean, please check this, okay? It's not so straightforward. We just need to do some work to show this, okay? Is this clear? Yeah, okay. So we are going to verify two properties here. Uh, okay. This is true for all a subset of E. And so what are the two statements that I want to verify? The first one is that mu of E is equal to 1. The second is that mu of E intersection J is bounded above by the size of J per S for any interval J. So there comes our mass distribution. Okay. Um, Once I verify item number one, I'll see that the S-dimensional Hausdorff measure of E is bounded above by 1. Yeah. And from the second inequality, I apply the mass distribution principle, and it will tell me that you have a lower bound on the S-dimensional Hausdorff measure, and it's going to be exactly 1 in this case, which is how we are, confirming that the S-dimensional Hausdorff measure of E is actually 1. Okay. So yeah, maybe I'll just mark this once 1 and 2 are verified. I'll be simply redoing the calculation that I've done earlier. Mu of E is bounded above by the sum of, say, some JIs, where this collection JI is a cover for E, and this is bounded above by sum of J per S for any cover of E. And then, from the definition of the S-dimensional Hausdorff measure, I have this inequality to be true. Yeah, and combining with the other inequality, I see that with, let me call this one, no, say a 3. 1 is already there. We see that, and that would complete the proof. So I just have to verify these two properties. I guess among the two, verifying the first one is somewhat easier. So does this answer your earlier question, by the way? So you can see that the construction of the measure mu is very much related to, where the mass of F or the mass of E is concentrated. Yeah.
Getting some more of it.
Right.
The
Property.
second property, that interval is arbitrary.
No, it's true for any interval.
Any-
Yeah, I mean, that should be true for any interval, right? Then only I can run this argument.
Right.
Yeah. Okay, so proof of one. Suppose we cover E by, net intervals. Let me call this collection S. Um, yeah, let me call this collection S. And in view of the net property, between the net intervals, if I take two net intervals in this collection, say, if I and I prime are in S, then either I intersection I prime is empty, or I is contained inside I prime, or I prime is contained inside I, right? So that comes from the net property. Now, um, if if these are if I is a subset of I prime, then I'm going to just remove I from the collection. Okay. Even then, I am going to I'll be left with the cover of E. Yeah. Um, and by removing these smaller intervals in this fashion, I can always assume that whenever I take two intervals I and I prime in the collection, if they are distinct, then I intersection I prime must be empty. Yeah. Now, again, since we have, I think I feel like I'm going through the argument as yesterday. So since E is compact, I can also assume that the psi, I mean, curly S is a finite collection of intervals. Now what do I do? I choose a J naught in this collection that has the smallest length. Oh, sorry, I should be, I naught is the notation I have, that has the smallest length. Okay. Let me assume that I naught is a net interval at the kth level.
So to use the compactness, we will slightly extend each of our intervals on
Yeah, exactly. Slightly. I mean, since they are disjoint, there's ample amount of gap between them. Yeah. So let I naught be in the kth level. Okay. Or sorry, maybe I have already a notation for that. Let me choose I prime to be the parent of I naught. Okay, that lies in the k minus 1th level. Okay, so I prime lies inside curly I k minus 1. And since I have assumed that distinct intervals must be disjoint from each other, and since this collection form a cover for my set E, um, I can immediately see that every other children of I prime must be there in the collection curly S. Yeah. I mean, if this is I prime and say this is my I naught, then there are the other children of I prime, right? They must be there in the collection as well because overall they form a cover for my original set. Yeah. And um, yeah, and I prime, of course, since I naught is there, none of its parents cannot be there, can be there in this collection. So these guys must also be there in the collection.
Why can't I have all children of I naught sigma? Oh,
I have assumed that I naught is the has the minimum length. Yes, thanks for that. So yeah, so that you cannot have childrens of these guys inside the collection because I naught is supposed to assume to be the an interval that has the minimum length in the collection. So let me. These are I1 and I2. Then it is clear that every children of I prime must be in curly S as well. So now I replace, this whole collection, all the collection of all children of I prime with just I prime in the collection S. With I prime in S. Now, when I do this, I have to take into consideration, like what happens to the sum, right? But you see that the sum of the S power of the sizes of i's are left undisturbed because we had a condition in the definition, right? So now recall, while doing so, recall that the sum of all I to the power S, where each I is a child of capital I, and I is in the kth level. So this is same as the size of I prime to the power S. This is why we had that assumption. Yeah. So if S1 is the, or curly S1 is the new collection that I have obtained, then for this new collection, I see that the S sum is same as the S sum for the old collection, right? And again, I keep doing this business, and each time I modify the collection so that it contains net intervals of larger and larger length, right? And finally, I'm going to reach the unit interval 0, comma 1. Yeah. So repeating this process, say moving from SK to SK plus 1, by replacing the collection of children with some parent from a higher level, um, I finally reach Sn for some large enough n with just one interval 0, comma 1. Yeah. Since the S sum has been left undisturbed in this modification process, um, we also see that the S power of S is same as and that's just 1. Okay, so what have I done here? I started with an arbitrary collection for E, and I have modified the collection in such a manner that I am. I mean, I keep removing things. Um, I mean, I keep removing quite a lot of intervals from the collection. Replace that with just one interval, and then you do this like so many times, and finally I reach the unit interval. And using this observation, I see that the S sum for my original arbitrary collection must be equal to 1. Yeah. So with that, property 1 has been established, right? Because now I just have to use the definition of mu of E and this whole argument. Yeah. Is this clear? Great. Okay, so that verifies property number 1. Now property number 2. So by slightly modifying the proof of property number 1, I can actually see that whenever J is a net interval, right, mu of E intersection J must be exactly equal to the Sth power of J, S power of the size of J. This is true as long as J is a net interval. Because for that collection, I mean, I do the exact same argument. It's just that if I'm working with E intersection J, I will go only up to J, right? And then the S sum of the arbitrary collection will be same as the Sth power of the size of J. So this identity, I mean, in fact, the inequality replaced with this inequality will hold as long as J is a net interval. So that's immediate from the proof of the first property. I want to make use of that observation. I want to use that, okay, now if I'm working with an arbitrary interval, can I somehow use these net intervals to compare, to measure the size of E intersection J? When J, what was the name I gave for the collection of all net intervals? That was curly F, right? Isn't it curly F? It was curly F. Curly IJ was the collection of net intervals at the jth level, and then the union. Yeah. So now I take an arbitrary interval J. Our goal is to recall to show that this is bounded above by the size of J per S. Now, I'll begin by making few reductions. The first reduction is that by chopping off the ends of J, I can assume that J's the endpoints of J are members of E. Okay, so that's the first assumption I'm going to make. That J is closed interval A comma B with both A and B coming from E. The second assumption is that by slightly thickening the ends of J, I can also assume that both I and B are, I mean, I is going to be the left endpoint of one of the net intervals, and similarly B is going to be the right endpoint of some other net interval. Okay. So by approximating or by slightly thickening, Okay. And the proof is divided into several steps. The first step,
And how you could get
yeah, thanks for asking that. So let's think, right? I mean, you're okay with this step. Yeah. Now, in the see, if A is in E, right? Now A is going to be contained inside these net intervals of smaller and smaller length, right? So if I fix an epsilon, say, then I can look at, I look at net intervals of length that are smaller than epsilon. Yeah. Then I can find one net interval. Say, take one of those net intervals that's containing the point A. The left endpoint of that interval is going to be epsilon away from A at most. Yeah. And um, yeah. Now, if I look at, uh, what do I want to say? Yeah. Now I just think of J as, suppose A epsilon is that endpoint. Then I'm going to think of J as A epsilon to B. Okay, we'll talk about B later. So for that interval, I'm going to prove this.
okay, yeah, yeah, yeah.
Yeah, then the difference is just epsilon. And
Yeah.
then, yeah, exactly. That's clear, right? Yeah. So which is why I've written approximating here because, yeah, you approximate J by intervals of this form, and then you prove this inequality for all those intervals, and then you get back to J in that fashion. Okay. So suppose I be the smallest interval, the smallest net interval containing J. And say I comes from the kth level. So let me draw J here, sorry, I here, that's I. And my J, say something of this form. I look at all the children of I, okay? Say it's of, actually, yeah, say it's of, so these are the children of I, okay? Then now this is J. So suppose J intersects IQ, IQ plus 1 all the way up to IR. All of these intervals are members of the kth level net intervals. And sorry, k plus 1 level net intervals. And all of them are children of I. Each a child of I. So this is going to be IQ, IQ plus 1, and this is IR. Now using convexity arguments, I'm going to show this claim. Okay. So I claim that in this setup, J intersected with IQ to the power S plus IQ plus 1 to the power S all the way up to IR, but it's not necessary that J covers the whole mass of whole length of IR. So I have J intersection IR over there. And I claim that this is bounded above by the size, the nth power of the size of J. Okay. Let me postpone the proof of this claim. But assuming the claim for now, let's try to, verify this goal. Okay. Have I lost you people already or? Okay. So in this case, okay, assuming this claim, I'm going to look at two cases. So as you can see, when I want to find out the measure of E intersection J, I basically want to find out what is going to be the mass of um, IR intersection, IR intersection, I intersection E for all those IIs that are completely covered by J. And then I have these two portions, right, which are not completely covered by J. Yeah. So let me divide this case, let me divide this scenario into two cases. The first case is when both IQ and IR are completely covered by J. So that is IQ intersection J is same as IQ, and IR intersection J is same as IR. In that case, so there are two cases here. In this case, mu of J intersection E is the sum of mu of I intersection E, where I varies from Q to R. And we have already observed that for net intervals, the measure of E intersection II is same as the nth power of the size of II. So this is equal to the size of II intersection E and the size of sum of the size of the nth power of II. And from the claim, I see that this is bounded above by the size of J. So the second inequality comes from the claim, and the first comes from this identity, which I'm going to call, I don't know, say star. Yeah. And in that case, we have we can establish the goal, right? Now case two. So in case two, either IQ intersection J is not completely IQ, or IR intersection J is not completely IR. without loss of generality, let me assume that only the first case, the first equality fails. So in this case, now in this case, I'm going to look at IQ intersection J. Right now, IQ intersection J is going to be this region. Well, in this picture, so this picture is a bit misleading because here it completely covers IQ. Let me assume that this is my J. Okay. Is this visible over there? Yeah. So IQ intersection J is going to be this region. This region. Right? Now I'm going to run this whole algorithm with J replaced with IQ intersection J now. Okay. So the immediate net parent of IQ intersection J must belong to IJ, curly IJ. Now, what do I mean by that? Actually, it doesn't matter. Let's see. So if I'm looking at IQ intersection J, and if I run this algorithm starting from this uh, this step, yeah. So then I'm going to choose the smallest net interval containing IQ intersection J. Now I know that I definitely contains IQ intersection J, but there might be something down the line, some other net interval down the line that might contain IQ intersection J. Yeah. So I doesn't have to be, I mean, so the I that we have over here might not be same as the that I that we are going to choose for IQ intersection J. Now I choose that I, and then I look at its children, and I'm going to have this claim again. Now in this claim can be applied even with J replaced with IQ intersection J. So then I get into these two cases again. If we are lucky, maybe this time I can get back to case one, and then I'll be done with it, because by case one I'll be able to verify this inequality for J replaced with IQ intersection J. Yeah, I'm going to write this down. Okay, so just give me a bit more time. So this way I'll be able to show that mu of IQ intersection J intersection E is bounded above by the size of IQ intersection J to the power S. Yeah. Then I go back to my original J. So by running the algorithm, and by algorithm I mean these two steps. This is step one, and this is step two, or step B. So running the algorithm, yeah, sorry. If we are lucky, we might run into reach case one. Okay. And then, by arguing as here, uh, I'll be able to see that mu of IQ intersection J intersection E is bounded above by the size of IQ intersection J to the power S. Have a question? Yes.
No, so and we are guaranteed to get lucky at some point by the assumption that J's left endpoint.
Yes, exactly, exactly, exactly. That's correct. Thank you for that. So, I mean, at one, like, if it's not going to happen in the first level or the first round, I keep, running this algorithm, and at some point, I have to hit case one because of this assumption that both the left and right endpoints of our original interval are left and right endpoints of some of the net intervals. Okay, so since this is true by the claim, um, I have, and that's bounded above by the size of, so the last inequality comes from the claim. Yeah. Okay, I think I've run out of time. So I'll skip the proof of the claim, but I mean, I've not like completely given you I've not properly completed the proof yet, but you can, work from here, right? I mean, you just have to verify why I should, run into case one at some point. You also have to verify why this claim is true. Now, as I was saying, you have to use some kind of convexity argument here. And um, uh, there are two cases that you can look at. Um, yeah, maybe I'll just, this is actually an easy exercise. You just have to play around with it, okay? So I'll just leave this as an exercise. And if you have any questions, you can just come back to me tomorrow and then we'll discuss it. Yeah. Okay. Questions? Sir, you seem to have some questions. M has no role to play. Yes. The Cantor construction. Yes. No, see, but okay, so you're choosing M to be equal to 3 for all I. Sorry, M equal to 2, right? You meant M equal to 2. Yeah, 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 yeah. Yeah. So yeah, if I do that, then yes, 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 yes. Okay, great. So you were saying, you're talking about the other measure. You were saying that there might be some other way you can construct this measure. Right, right. Yes, 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 yes. Yeah, yeah, right, 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 right. Yes, that's right. So in a way, I mean, if I'm looking at the Cantor construction, you're saying that in the first round, see, I'm dividing, I mean, the total mass is 1. I'm divide the total mass into 2. Yeah, put half and half out there. Yes, exactly. So it's the same. It's the same. It's the same. Yes, 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 yes. Yeah. Okay, great. Thank you. It's neat, isn't it? It's really neat. Yeah.